All right, so this next section we're going to look at is nuclear chemistry. Do you know what this picture is of right there? Well, if you can read the words below, you sure do, but hopefully you haven't looked at those yet. You can probably tell it's a picture of a brain, and depending on what field of medicine most of you plan to go in, you might actually work in radiology and look at and work with patients in terms of those who need x-rays and CAT scans, things like that. And this is basically a map of the brain. And I'm not a doctor, so I'm not going to analyze it, but what we're going to talk about in this section dealing with nuclear chemistry is what allows us to view these type of images, and that is X-ray beams. X-rays are a form of, do you know, radiation. Okay, so to be able to talk about radiation, we have to understand what's happening. Where does this radiation come from? And that is, right here, a radioactive isotope. Radioactive isotopes are isotopes like we've learned about before, but these are special in that they have an unstable nucleus versus a more stable one. So what happens, as you can see here from the definition, if you've got an unstable nucleus, that nuclei really wants to become stable, and it does that when it emits radiation. And after it emits the radiation, it becomes more stable. I think about it when I think of little kids playing the game hot potato. You've got a hot potato in your hands, and it's really hot, and you're jumping all around because it's so hot, so hot, so hot. And once you let go of that potato, then you stop jumping around. And the little kid playing that game, when he's holding the hot potato and moving all around and very crazy, unstable, that would be like my unstable nuclei, versus after he's let go of passed the hot potato along, he then becomes more stable. Okay, so in terms of stability, let me erase this, and let's look at the chart right here. So this is just 3, okay, some elements. There are, as you know, how many elements on the periodic table? Well over 100. And most, if not all of them, also have radioactive forms or radioactive isotopes. These are 3, just 3, magnesium, iodine, and uranium. And magnesium and iodine actually have stable forms, meaning they're not emitting radiation. They're stable as they are. That's magnesium 24 and iodine 127. So that is magnesium with a mass of 27, magnesium with a mass of 24, iodine with a mass of 127. Interesting to note, uranium, you've probably heard of uranium before. Uranium has no stable isotopes. They are all radioactive. All right, and then the radioactive ones, for magnesium, there's 2, magnesium 23 and magnesium 27. We're going to talk about these numbers here in just a second. And then for iodine, 125 and 131. And finally for uranium has these 2. Now, just because there's 2 listed here for magnesium, iodine, and uranium doesn't mean that every element has 2. Okay, this just so happens that for these 3, they have 2. They can have 1, they can have none, they can have 4, but these 3 happen to have 2. Now let's talk about what these numbers mean real quick. So, we've looked at protons, neutrons, and electrons before. And in terms of formatting, when you are talking about or representing an element, in this particular format like I just wrote out, the number and the number here, we'll just call that X, okay, that's my symbol. The 2 numbers obviously mean something. Now, what do they mean? Well, the bottom number always remains as is and is the atomic number. The top number can vary and will vary based on which isotope you have. And so this is the mass. And so if we just look here at magnesium, as I just said, the bottom number is 12, and that's the same for all 3 isotopes of magnesium because magnesium always and only has an atomic number of 12. The mass, the number on top, 24, 23, and 12, that varies because these are 3 different isotopes of magnesium. And we've talked about isotopes before, so I'm not going to waste your time going into it. But just as a reminder real quick, Number of protons is always equal to the atomic number. So for magnesium, protons would be 12. Number of electrons in a neutral atom, that happens to equal the number of protons, so that's 12 for magnesium. And then depending on which isotope, let's just pick one of the three, let's do this last one here. The number of neutrons is equal to the mass, 27, minus the number, which is 12. So, can you do that math in your head? Magnesium 27 has 15 neutrons. And as a reminder, again, different isotopes have different mass numbers, and more specifically, it's the number of neutrons that varies. Protons and electrons will stay the same in different isotopes. Okay? And we can represent the different isotopes either with the formatting like this or with the name and the mass after it. Okay? And again, the reason we wouldn't say like uranium 92, 238 is because uranium's always 92. I don't need to repeat that. But when I'm talking about or referring to an isotope, you need to know which isotope is it. Uranium with a mass of 235 or uranium with a mass of 238. Okay, so that radiation that I just talked about being emitted from an unstable nuclei, well, here are the different radioactive, when we talk about particles being emitted, here's what your choices are. We've got an alpha particle, which just so happens to match what a helium atom looks like. We've got beta particles. Beta particles, essentially an electron with a lot of energy. Electrons have no mass, that's why the 0 is there, and electrons are negatively charged, so that's why the negative one. We also have a positron, which you can represent in one of two ways. Positron gets the B for beta, the beta symbol, but with a positive because it's a positron. Or you can kind of match what we did with the beta, where you have, it's an electron. It happens to be a positive electron. Mass of 0 because it's an electron, but because this is a positron, instead of a negative one, it has a positive one charge. And then finally, gamma. Gamma, there's the Greek symbol for gamma. There's no numbers here. No numbers here, no numbers there, because it's actually energy. Just energy, high energy released from the nucleus in the form of electromagnetic radiation. We're going to talk about these all more as we go through this lecture, but I wanted to introduce them to you on this. Okay, so let's talk about, I think this is pretty interesting, the different particles and what kind of shielding you need. Everybody's had an x-ray in their life, whether it's been in maybe a dental office or, in a hospital or a doctor's office, and the technician, they wear the lead apron. Well, that's because they're trying to protect themselves from overexposure to radiation. And again, in a dental office, typically they put like a lead apron on you when they're x-raying your mouth. And that's, again, to protect your organs from unnecessary radiation exposure. Clearly, your face is being irradiated when you have an x-ray of your mouth, but, a couple of times, once every 6 months or so, isn't a big deal. The technicians do it because, again, think about how often a dental hygienist or a technician is exposed to dental x-rays over and over and over all day long. So overexposure can lead to problems. So they don't want to have problems with their bodies and health, so they wear shielding, protective shielding. And since the rest of your body, you're the patient in the dental chair, since the rest of your body isn't being irradiated, not needed to have an x-ray, why not just cover it and protect it just in case? Okay, but let's talk about the different things. So alpha particle, you can see here how far they travel, 2 to 4 centimeters. A couple of inches, guys. It's about what that's equal to. Beta particles travel a whole lot further, 200 to 300 centimeters. So that's between 2 and 3 meter sticks, okay, meters in length. And then gamma travels a very, very long way. 500, that's not miles, 500 meters, 500 meters. That's like a half a kilometer. So that's a distance you would drive. Huge differences in far as how far they travel. You can see, again, tissue depth, very different. Alpha being the least penetrating, gamma being the most. And again, shielding. Piece of paper will block an alpha particle. Beta, just wear, thicker clothing, a lab coat even, or gloves. Versus gamma, you need a lead apron or thick concrete. Typical source typical source, not the only source, but just the most common. To get an alpha particle, you're typically looking at a radium-226 unstable isotope. For beta, we use a lot of times carbon-14, and for gamma, oftentimes technetium-99m. What's the M mean, you might ask? It's called metastable, but basically it's a technetium-99. So, just a picture here of a guy walking down the street. What's going to protect him from an alpha particle? His backpack, his shirt, that'll protect from an alpha. Beta will go through the shirt, but probably, not too far into his body. Gamma will go straight through, like an X-ray would if I tried to X-ray this guy's body. All right, so let's look at some actual chemistry. So here is an unstable uranium-235 atom. It's unstable. I think that's what my little guys here are supposed to be representing. Think about the hot potato, okay? And what happens, it releases a particle and forms a more stable isotope. And it just happens to actually be something else. Because if you start with uranium-238 and you remove a helium, when you do the math, all that's left, because I still have to obey the law of conservation of mass. Okay. The numbers still have to add up to be the same. But regardless, what I'm showing up here is I get a more stable isotope, and it releases alpha particles. Now, are alpha particles all that dangerous? Again, we just saw that they can be blocked with a t-shirt. So you can protect yourself, but still you don't want to be overexposed or unnecessarily exposed. Now, let's look at, let me erase that, guys. Let's look at this stuff down here. In fact, let me draw a line. And let me show you how we balance nuclear equations. Well, this one's already balanced, but let me prove to you how it is balanced. So again, law of conservation of mass. Matter can't be created or destroyed. My numbers have to be the same. So for instance, if I have uranium-238, the top number is 238, the bottom number is 92. So I have 92 protons, because that's the atomic number. And when you subtract these two, I get 146 neutrons. You don't honestly even need to look at the neutrons, but we're looking at the numbers. So in fact, let me just erase that. The numbers have to add up to the same. So if you think about the arrow dividing your reactants on the left, your products on the right, my total numbers on the left, on top, 238. Total number on the bottom is 92. And that was pretty obvious, right? It's the only thing over there. But on the right-hand side, they have to add up to the same totals. So 234 plus 4 is 238. 90 plus 2 is 92. So the law of conservation of matter is not disobeyed. It's still, even though we're talking about nuclear chemistry, and even though we're talking about turning one element into something else, the law of conservation of matter still applies. And so when we balance these and look at these things, the numbers still have to always add up to the same total. Okay, here's another one. This is carbon-14. Carbon-14, as it shakes and vibrates, as the picture shows, but as it's unstable, becoming more stable, it releases, this one gives off a beta particle. Now, we're not going to get into why certain isotopes give off alpha versus beta. You would be given that information or be able to figure it out just by balancing an equation, okay? But as, just to note that different isotopes do different things. Some give an alpha, like the uranium, some give a beta. But keep in mind, this also comes with large amounts of energy typically as well. That's why we think of, and it's true, that radioactive substances, are harmful. Now, my brother was just talking about the numbers and the math. Okay, let's look at this equation here. I've got carbon on the left-hand side all by itself. Total is 14. On the top, bottom number adds up to 6. The right-hand side has to add up to the same. I have 14 plus 0, which is 14. That's good. I have 7 plus a negative 1, or in other words, 7 minus 1, which is 6. So again, I'm still okay. I increased, though, which is interesting, the atomic number, but that's because what was being given off is a beta particle, and I've got to still obey the law of conservation of matter. All right, so here's a practice one for you. Write an equation for the decay of potassium-42, which is a beta emitter. So as I said, typically you're told exactly what it gives off. So a beta, remember, is an electron with a mass of 0 and a charge of -1. Sorry, this is a little off here. So if I have potassium, my formatting got a little off here, you guys, sorry. If I have potassium's number is 19, its mass is 42. And I know that because of what the problem just told me right here, it's going to decay and give off a beta particle, which this is the symbol for beta. The question is, what else? What's the other missing piece? Because that doesn't clearly add up to the same numbers. So to write the equation, to finish the equation, I got to do the math. So divide your equation, reactants on the left, products on the right, and the numbers have to add up to the same. So my top needs to add up to 42, which means my missing piece, whoops, my eraser's too big, sorry guys. My missing piece must have a top number of 42. And then now let's look at the bottom. It has to add up to 19. Well, positive 20 plus a -1 or 20 minus 1, that's 19. So now we need to go look at the periodic table and figure out what has an atomic number of 20. Well, it's calcium. Okay, calcium. So again, sorry, my formatting's a little off here. It didn't convert over correctly. So my balanced nuclear equation for the beta decay of potassium-42 is this. Okay. All right, now let's look at these other ones. And again, let me kind of fix the formatting, at least on this one. Okay, so it's manganese, which is Mn, not to be confused with magnesium. Manganese with a mass of 49 and atomic number of 25. It decays to give off a positron. Positron, 0 mass, +1 charge, plus what? Well, plus what? That's going to be easy to figure out. Let me fix that. Okay, so let's figure out what we're missing. 49 and 0, there, divide my equation. The sum has to add up to 49. So 0 plus what is 49? Well, 49. And then the bottom has to add up to 25. Well, my positron, this is a +1 down here. So in other words, 25 minus 1, my bottom number has to be 24. And I can always check that. 1 plus 24, yeah, that adds up to 25. And then we've got to go look up on the periodic table. Right now I'll just give it the symbol X. I'm going to let you finish this one. You go to the periodic table and look up what has the atomic number of 24. And that's your symbol that goes there for X. All right, finally, let's talk about gamma radiation. Gamma is actually pretty easy in the sense that the numbers are 0, doesn't have mass, doesn't have charge, but it's at a huge amount of energy. And as you can see right here, energy is emitted from an unstable nucleus indicated by the following mass number. The mass number and the atomic number of the new nucleus are the same for the two of them. So for instance, technetium, remember that technetium-99m, that metastable? So very, very, very unstable. M indicates that. And now I've got a more stable technetium-99. So we use the M to depict the difference between these two isotopes. M, very, very unstable nuclei. It releases gamma, and it forms the more stable, the slightly more stable technetium-99. And then here's my symbol for gamma. It's the Greek letter, and then 0, 0 for my numbers. Okay, so here's just a summary of the different types of radioactivity. As you can see, some different things here that are interesting that we've talked about some. Down here at the bottom is the summary of the table. Again, that doesn't match your chapter necessarily, but that's okay. This information is correct. It's just not from chapter 4. So some stats up here. When an alpha particle collides and cools down, it will then become a helium atom by extracting 2 electrons from its collision partner. Interesting, huh? The emitted electron gets captured by its collision partner. A positron eventually collides with an electron, and gamma radiation is given off. And when a gamma ray is absorbed, it usually causes the loss of electrons from the absorber and subsequent chaos, such as bond breaking. That can happen in your cells. Okay? What happens when you destroy a cell in your body? Well, eventually, you can lead to death. So that's one of the reasons that gamma is so bad for you in terms of the exposure. So, moral of the story here is a lot of times they're actually tied together, and you won't just necessarily have alpha. You can have multiple. You could have alpha and beta. You could have combinations of all different things. So how do we measure radiation? Well, we use a Geiger counter. A Geiger counter uses ions that are produced by radiation to create an electrical current. Some of the radiation units that a Geiger counter would measure, for instance, length is measured in meters, as we know, and many other units. But for radiation, we measure it in Curie. You know who that might stand for? Madame Curie. That's a whole history lesson in itself. Anyways, so the Curie is one of the radiation units. It measures activity as the number of atoms that are decaying in 1 second. A rad, which stands for the radiation absorbed dose, and that's based on how much radiation is absorbed by tissue in your body. And then a rem, radiation equivalent, and that's the measurement of the biological damage that can be caused by the different types of radiation. So I think these are all pretty interesting. Probably the damage done is most interesting to most of us, I suspect. How can you be exposed to radiation? We talked about X-rays. Everybody probably knew that. There are natural sources as well, just living on planet Earth, being exposed to the sun, even though it's sometimes the middle of winter and it may feel like you're never going to see the sun again, you're exposed to sun. Additional things, medical and dental procedures, for obvious reasons, X-rays, for instance. Traveling in an airplane. I did that just this morning, and I had a higher level of radiation exposure than I would be if I was just on planet Earth. Why do you think that might be? Well, one of the reasons is you're a lot closer to the sun. Radon. Depending on where you live in the country, you may have higher levels of radon. You might be exposed to it. The house I actually own now had high levels of radon before I moved in. I did a radon test, found that out, and was able to get the remediation done before I bought the house and moved in. So maybe you do or don't. Maybe you know about radiation, maybe you don't. Smoking cigarettes, obviously that's very bad for you for many reasons, but it also exposes you to radiation. And then even just eating. Well, how in the world does eating expose me to radiation? Well, I'll have you know, a lot of food is irradiated. For instance, fresh strawberries. I'm living in, outside Chicago. I don't typically have fresh strawberries, especially in the winter time here, that can be picked on a farm, but yet they sit on the grocery store shelf. Well, they're picked and sourced somewhere else in the middle of winter, and they're irradiated to keep their shelf life longer. And then I eat those strawberries. So guess what? Exposure to radiation. Here's some interesting things in terms of radiation doses used for diagnostic and therapeutic procedure. So if you're just trying to diagnose, for instance, if you've got maybe liver cancer, you can see the REM dose is only 0.3. If they're actually trying to treat your cancer, clearly radiation a whole lot higher. And I think that makes sense to most of us, right? Here's some interesting facts. Just the average annual radiation received by a person. It's in millirems. Remember I talked about rem on the previous page. This has an M in front of it for milli, the prefix milli. And you can see just by living on planet Earth how you're exposed to different sources of radiation, even cosmic rays. Isn't that crazy to think about? X-rays may or may not have these in a given year, but if you do have one of those or multiple, you can see what the dosage. And even watching television, as I talked about air travel, and then radon, it says varies widely. That's because, well, depending on where you live, you may have higher or lower exposure rates. All right, so let's talk about half-life. Half-life is the amount of time for the radiation level to decrease, or we also call it decay, to 1/2 the original value. Now, let's take, oops, I think my numbers are a little off here, you guys. Okay, so what we've got going on here, because this is a little confusing, I'm starting with iodine 131, which just happens to be the unstable radioactive isotope that's used in thyroid diagnosis and treatment. So iodine 131 is radioactive unstable. It decays, oops, I didn't do my numbers, sorry. It decays to xenon 131, which means if I do the math and solve for my missing piece, do you remember what that guy was? That's a beta particle. That's a beta particle. That's my electron, essentially, high energy electron. Okay, I digress though. I just wanted to practice showing you another equation. Let me erase that. So my reactant is the iodine 131. My products are these two particles. But I'm going to measure this in terms of the mass of xenon versus the mass of iodine. Okay, and in fact, let me give you some numbers as well in terms of, okay, I'm going to start with, how much. So, let me get my numbers here. All right, so imagine, I've got a little missing piece here. Imagine you're starting with 20 grams of reactant, no product, and after the first half-life, that 20 grams becomes, you can see right here, 10 grams. This is of the iodine 131. The reactant, okay, that's decaying. I'll talk about the product in just a second. Okay, if you start with 20, after the first life, you're only going to have 10 of the original left. After another half-life, well, now you're down to just 5 grams. After another half-life, you have just 2.5 grams, and so on and so on and so on until you have no iodine 131 left. And so regardless of what you start with, whether it's 20 grams or 2 million grams, every half-life cuts the amount of the reactant, cuts that in half, and therefore subsequently produces that amount of product, okay? So let me do product then. So initially, no product. We're going to do product in blue. Product was my xenon, okay? Reactant was my iodine. So initially, you start with no product. After the first half-life, I lost 10 grams of reactant, therefore I produced 10 grams of product. After my second half-life, now my numbers are going to match here. Okay, I lost 10 plus I lost another 5 because 10 went to 5. So I'm down, started at 20. I only have 5 grams of reactant left, so they always have to add up to the same amount. Therefore, now I have 15 grams of product. 5 plus 15 is 20. Okay, remember law of conservation of matter. I can't create or destroy, so it always has to add up to the original 20. Another half-life goes by, and my 5 reactant went to 2.5 reactant. So I added 2.5 to my product total, and again, these two have to add up to 20, and they do. I like to think about it, I like to cut things in half, so I always take the reactant and just cut it down. Every time you go through a half-life, the amount gets cut in half. 20 to 10 to 5 to 2.5, and then to 1.25 to 0.62, okay, until we're at 0. So that's what half-life is in terms of quantities of reactants versus products. Now, what about the time it takes? Well, every substance is different, okay? It's not in terms of cutting the amounts in half. It's always, regardless of what the substance is, regardless of what you're producing, half-life is the amount of time it takes to cut it in half. But what does vary is the actual half-life, okay? The time it takes, we call that the half-life. How much time it takes, that's the half-life. That varies based on what you have. For iodine 131, it happens to be 8 days. So after 8 days, if I started with 20 grams of the reactant iodine, after 8 days, I'll only have 10 grams left. After another 8 days, or a total of 16 days later, that gets cut in half, and I only have 5 grams left. After another 8 days, which is a total now, 8 times 3 is 24, I only have 2.5 grams of reactant, unstable, radioactive iodine 131 left. And so you just add them all up, add the half-lives up. 8 plus 8 is 16, plus another 8 is 24, and you could keep going and going until you're completely out of iodine 131, or reactant. Okay? And here it shows in a graph form. It's good to read, but I typically don't use a graph when I'm trying to just basically calculate a simple half-life. Okay, half-lives are interesting. They vary quite widely. Some substances have half-lives of several seconds. Some have half-lives of millions and millions of years. So they're all different, just like elements are all different, their half-lives are all different. So here's some radioisotopes that are naturally occurring, and they tend to have the longer half-lives, versus those used in nuclear medicine tend to have shorter half-lives. So for instance, here's the ones with the, draw the line here, below the line. These guys are used in medicine. Notice their half-lives are hours and days. Versus natural occurring, you've heard of carbon-14 dating, probably, may not know really what it means, but carbon-14 is the radioactive isotope, one of them, of carbon, and it's got a huge half-life. Well, we use that to our advantage when we're trying to carbon date something, like an artifact or a fossil. In medicine, for instance, you go in to have your thyroid assessed, and you have a nuclear medicine study done, and they actually give you some iodine 131, and it's radioactive. But thankfully, it's not radioactive for 5,730 years. It's only radioactive for 8 days. So they give you a little tiny amount of iodine 131, and the reason that one works so well for thyroid is because your thyroid processes iodine. Whether it's radioactive or not, your body doesn't know. Your body sees iodine come into your system, and it sends all the iodine to your thyroid for processing. And if it's radioactive, it's going to be emitting radiation that can be measured and detected. And if it's not working properly, it's not going to process that iodine. So when they do the nuclear study, they can tell whether your thyroid and what it's doing, how it's behaving. But you don't want to have something that has 5,000 year half-life, or you be radioactive forever. Be crazy. So you want things with relatively short half-lives in medicine, and that's why we pick and choose the things that we do. So radioisotopes with short half-lives are used in nuclear medicine because they have the same body chemistry as the non-radioactive. That was the example I just gave. For instance, the thyroid scan. Okay, this actually happens to be a picture of my thyroid. I had an iodine 131 study done, and since I teach this class, I think it's interesting, I shared it. Okay? Again, iodine, thyroid handles, whether it's unradioactive or radioactive, your body sends all iodine atoms to your thyroid. Okay. And you guys might find this really interesting. Most of you want to go into medicine. I'm going to give you a minute, or hit the pause button, even better, and look through some of this. I think it's really, really interesting. Different elements are used for different applications in medicine because, again, your body takes them in and they send them off to different organs, different areas for metabolism, or that's, for instance, like calcium goes to your bones. So that would end up in your skeletal system. So take a minute and read through this, and then hit the pause button, and then come back when you're ready to continue. All right, we're back. The other part of this is to talk about fission and fusion. And as you can see here, fission is the opposite of fusion. Fusion, everybody knows what fusing means, right? Merging things together, putting things together. Fission is the opposite. It's the splitting apart Fission is splitting apart. So this is, I've got a big unstable that looks like uranium-236, and it breaks apart into many smaller particles. And because it's unstable, radioactive, as it does this, it also gives off lots and lots of energy, and this one happens to give off neutrons as its radioactive particle. You can see down here, definition in nuclear fission, a large nucleus, something that has a very large nucleus, typically like uranium size. It's bombarded with a small particle, and the nucleus splits into smaller nuclei and several neutrons. And here's the kicker, guys. Large amounts of energy are released. Insanely large amounts of energy. Insanely large. So for instance, I don't actually do this in my home, but uranium-235, bombard it, take a little tiny neutron, and at a very, very, very high speed as well, you take this little tiny neutron and you hit this crazy unstable uranium-235 or 236, and it splits apart. Okay, for a second it holds on to it. Okay, that's what this is showing here. But very quickly it just goes and splits apart into all these smaller things, and again, large and large, insanely large. I can't emphasize that enough, amounts of energy. Now, fission and fusion, one is done on the surface of the sun, one is done at nuclear power plants to generate energy. I'll let you figure out which is which. However, I'll just tell you this. It's enough energy, obviously, to heat the sun. The sun heats planet Earth. And then nuclear power plants generate enough energy to boil water. The water, in turn, turns turbines, becomes steam, really. The steam turns a turbine, and that is converted into electrical energy and powers homes if you live near a nuclear power plant. All right, so here's what's going on in the nuclear power plant. Okay, and so if you were guessing fission and fusion, so fission is what's done inside a nuclear power plant. You can see everything I was just talking about right here in terms of how it works. This is what we get in our house, and that's really most of us all we care about is we've got our electricity. But there was many, many steps and lots of things involved to be able to actually get that to happen. And so as you can see, in nuclear power plants, fission is used to produce energy. We've got control rods. The control rods, that's the source of where, for instance, the uranium, radioactive uranium would be. They absorb neutrons, so they're hit with neutrons. And they slow and control chain reactions of fission. So a chain reaction, you start one reaction here, hit this one, but then notice these three little neutrons that are produced, and you can never just have one atom of anything. It's way, way, way too small. You're going to have a sample, and in fact, we call this a critical mass, but that's not important right now. So you've got millions and billions of uranium atoms, even in a small sample. So as one uranium atom gets hit with a neutron, it produces three more. Those three find more uranium, unstable, floating around very nearby. They hit those, and so on and so forth. It becomes this crazy chain reaction. And every single time you even just have one reaction, you get energy, and quite a lot of it. So imagine if you have hundreds and thousands of these chain reactions, each one producing a large, substantial amount of energy. And then here's the opposite, fusion. Fusion occurs at extremely high temperatures. Okay, I like to draw my little tablet. Fusion happens when you combine small nuclei into larger, so truly the opposite. I don't have something bigger making it smaller. Here I have small things combining to make a somewhat larger nuclei. And when this happens, again, large amounts of energy released. Happens on the sun, happens in our stars. And that concludes your nuclear chemistry chapter.